Dear students, today we are going to discuss experiment number 8. In last video, we have learned about experiment number 7, how to emulate a wind turbine. Okay, so after that, when you have got the mechanical power, that we are going to couple it to any uh, generator. Okay, via a gearbox. Okay, generally we are going to use a gearbox for induction machines. Okay, for induction machines. Uh, in case if it is a variable speed, then we are going to use permanent magnet synchronous motors. Okay, so if you are going to use a permanent magnet synchronous generator, then already you are going to use a permanent magnet, so you need not require any reactive power there. Extra reactive power, okay, is not required in the PMSG, permanent magnet synchronous generator. However, if you are going to use any, not any, if you are going to use squirrel cage induction motor, then it required a reactive power. In order to provide that reactive power, we are going to use a capacitor bank. Okay. Since sometimes the as I earlier also have discussed that it will the input speed may vary. Okay, even though if you are going to use a gate system, it will not give exactly 1500 rpm. Okay, so that is the reason why every time the frequency may fluctuate. So again, what is the condition? In case if you want to free from the frequency, just convert that power into DC, right? So this three phase power I am converting into the DC. Okay, so after converting it to the DC, this DC is also variable one, right? So now we want to maintain a fixed DC voltage. Okay, we call that as a DC link. Okay, so here we are going to use a uh, DC to DC converter. Basically, it may be a buck, it may be a boost, or it may be a combination of buck and boost. So basically, the working is we try to maintain the output voltage of this buck boost converter constant. Okay, that we call it as a DC link. Okay, DC link. From the DC link, we are going to convert, we are going to connect, we are going to give this DC link voltage to a inverter. Okay, inverter, and then we are going to convert this DC to AC. Now we don't know exactly what is the how much voltage it is going to generate. Okay, so it is fluctuating one, so that's why we have converted into the DC fixed voltage. So here the thing is we are going to use a step-up transformer. Okay, uh, so why we have to use a step-up transformer, we'll discuss it later. Okay, so we will be using a step-up transformer and then we are giving it to the load. So what is the output voltage, nominal output voltage three phase? That is 450 volts, right? So here, if you are going to take a boost converter also, how much we can able to boost the voltage? That is, today we are going to use a high gain boost converters. Okay, but every time we cannot use those converters because for every application they will not be applied. Okay, so instead of that one, at reduced cost, this is the best solution. Okay, that is converting this DC link voltage. Generally this DC link voltage will be up to 120 volts maximum, 60 to 120, like that. They may vary, it may vary. So 60 to 120. After that, depending upon the DC link voltage, whatever you are going to set here, okay, depending upon that one, your step-up transformer will work. Okay, say suppose you are going to maintain a 60 volts DC, then you are going to get here nearly about the 60 voltage. Say suppose, just I am giving an example. Okay, so it may be giving near about the 60 voltage AC. However, your load requires 415 volts, so that's why we are stepping up this voltage okay, to 415. That is line to line voltage. Okay. Now, coming, suppose this generator is not working. I need a continuity in supply to my load. In such condition, we are going to use a battery bank. Okay, we are going to use a battery bank. This battery bank again, it will be having a DC to DC converter. This DC to DC converter will be a bidirectional power flow. Why, sir? Because it should, whenever this is charging, at that time power will flow from DC link to the battery bank. Whenever it is discharging, then power will flow from battery bank to DC link voltage. Hope you have understand. So that is the reason why we are going to use a bidirectional DC to DC converter. I will repeat again. Whenever battery is discharging, then power is flowing from battery bank to the DC link. When battery is charging, then power will flow from DC link to the battery bank. Fine. So here this bidirectional, generally it will be a push converter, because depending upon the, again it will be depending upon the combination of batteries. Say suppose you have connected 12 batteries, 12 volt battery. If two batteries are connected in series, then hardly, suppose 24 volts battery, then how much it will give? If we are going to connect in series, it will give 48. Okay, but our DC link voltage is around 60 to 120. Then we have to step up, right? So this is how it is going to work out. Now, in simulation, I have not included battery bank, okay? And instead of CAG, I have used a permanent magnet synchronous generator. And here I tried to tune the parameters, but it doesn't fit exactly. But it is somehow giving some results. So I just want to give this as a demo purpose, okay? So let us go to the simulation. So this is your simulation. Already in experiment 7, we have discussed all these things. So from this, we are going to get a speed, that is mechanical input, and that mechanical input we are going to give it here. For that one, you have to give, you have to do some settings like what is your mechanical power, okay? So your mechanical power is, we are giving as a speed, okay? Fine, okay. Here I am currently taking this as my present model. Okay, this is your permanent magnet. And then again, what we have to do, convert this AC into DC by using a universal bridge, that is diode rectifier. Then we have used a capacitor to filter the AC components. Then we have used a boost converter to boost the voltage. Okay, and finally, here we are going to get the DC link voltage. Okay, whatever may the output of the buck converter, boost converter, DC to DC converter, that we are going to take it as a DC link voltage. From the DC link voltage, again I am giving it to the inverter, and this inverter will convert. Okay, inverter design already we have seen, okay, in the previous lectures and all. So I am not discussing all those things. Then we are going to convert that AC into DC. This is my load, okay. To this load, again I am calculating the line voltage and phase voltage. How to calculate the line voltage and phase voltage? Phase voltage means to a phase and ground. So here I have used a star connection, and I have taken out the ground. Okay, so this is my ground. So between these two, if I am going to take, then I am going to get the phase voltage. Okay, and in case if I am going to connect it, measure between the line to line, then we are going to call it as a line voltage. Okay, here you can see all these values. Okay, this is the line voltage and this is the phase voltage. Fine, this is about the simulation. We will try to run it. You can check here. You can check here. This is our phase voltage. This is our line voltage. So here we try to maintain a voltage of 800 volts. Okay, now we'll see the parameters here. Okay, so this is my duty cycle. Currently I am maintaining 0.7. Okay, 0.7 is my duty. Then I'm going to get the DC input to the buck converter, whatever may be the DC voltage. This is my DC voltage. Then buck out is this much voltage. Then this is my speed and this is my power. And this is the output parameters, that is how much VDC I'm getting for this duty ratio. This is a voltage DC VDC voltage, that is DC link voltage, and then this is my line voltage and this is a phase voltage. Remember, these two are RMS values, line voltage and phase voltage. Here we have calculated it in RMS value. Okay, this is my RMS values. If you want to check the voltage, see, this is the line voltage. Okay, and this is a phase voltage and this is a line voltage. Okay, this is a line voltage and this is a phase voltage. Okay, hope you have understand this concept. So I will just explain once again. In measurements also, this is a experiment number 7 results and this is experiment number 8 results. Okay, so here we have used a since we need to generate a mechanical power, so we have used a DC converter, DC motor here. So for that one we are going to give a supply through a buck boost converter. This is a three-phase supply converted into the AC to the DC by using a rectifier, and this AC we have given it to the buck converter. This buck converter by changing its duty ratio, it is going to give a variable output voltage. Okay, and this is a separately excited motor. We have given a separate source. Okay, and then whatever may be the supply we have given, from this one we are going to get speed, and I have given that speed, whatever may be the torque. Okay, speed, shaft speed, I have given it that as input to motor. Here I have used a permanent magnet motor, and these are my, after rotating, these are my power. Okay, how much power I am going to generate. Okay, here we have calculated this power. Okay, how to calculate the power again? Okay, here power is equal to torque into speed. Okay, here I have written the formula also. Power generated is equal to torque into speed. The electromagnetic torque, how much it is generating, into speed, that is nothing but your power. Fine. Next, this is the AC supply. AC supply, I am going to, we are going to get a AC output voltage, right, from the permanent magnet synchronous generator. Then we convert this three phase into DC. Okay, AC to DC. Then this we have used a push converter to boost the voltage. Basically, DC to DC converter. It may be a buck, it may be a boost, or it may be a combination of buck boost, depending upon your input variable. We can able to choose it. Okay, and that is input variable means input voltage. Then we are going to convert this DC into fixed DC. That DC we are giving it to the inverter. This inverter converts DC into AC, and this AC is connected to the load. That's it. So here we try to calculate the line voltage and phase voltage. This is our line voltage and this is our phase voltage. That's it. Same parameters I try to measure the parameters. Okay, so this is your duty ratio, change in duty ratio, you can able to observe from here. Then whatever with the buck which earlier we have used starting, that is buck input and buck output, and then how much speed we are going to get. After that, how much power we are going to generate. Then at here we are going to see the what is the DC VDC, that is DC link voltage, then line voltage, and then phase voltage. That's it.